Just can people on Zoom hear me? Hello, can people on Zoom hear me? What is this? That's this. Is this better? Yeah. How about I haven't turned on chat, have I? All right, can people on Zoom hear me? Why is there that sound? All right, I think this is set up. Okay. All right. I'm gonna go use the restroom before we get started. Do you mind washing my stuff? All right. That's good afternoon. Uh, Hello. Welcome back. All right. Okay. Good afternoon. How's everyone doing? All right. We've got some assignments. We've got the checkpoint that's due this Friday. LRB's lab is due this Friday. How are people doing on those things? Doing well? All right. One more lecture before, or two more lectures before spring break. All right. Let's get started today, shall we? All right. So today's lecture is going to focus on one specific algorithm. We're going to be trying to build an algorithm entirely from scratch, starting with some ideas that don't quite work and kind of build our way up to this. Kind of our goal for today is going to be to find the shortest path between two points in a graph. So let's just take a look at some of the ways we've already found paths in graphs. Okay? We've seen depth first search, where you just go from like one point and you look at each neighbor as you go. And we had breadth first search, where we kind of look in layers around the starting point. So which one do you think is better for finding the shortest path in each node? Depth first search, where you just keep going one step at a time, looking for anything new to look at, or breadth first search, where you go like one layer at a time? Breadth first? Why do you say breadth first is better? Yeah. Because each layer at a time, so you keep like the same layer you cover. Yeah, because we're looking one layer at a time, we look at each node at the innermost layer that it's in. So we kind of get the shortest path. Now, we should be looking to see exactly what we mean by this. So let's look at a few considerations. First, correctness. Does it work for graphs? Yeah, they do find paths. Does one yield better results? Yes. Breadth first search does get you paths that give you the fewest edges. Is one more efficient than the other in terms of time cost? I don't really think so. They're kind of very similar to each other. At the very least, they have the same O bound, and that's as close as I need to worry about. Yeah, do you have a question?
From like the perspective of the main difference, just be that BFF also gives you the shortest path, but it takes more like more memory.
Yeah, kind of. We'll actually get into that really soon. Yeah, space efficiency is the one point that you're about to consider. Yeah. If you look at the space that's used for these graphs, you notice that depth first search actually takes a lot of memory if your graph is very spindly, if there's not many different nodes. Kind of the reason why is that in the depth first, you kind of keep following paths and keep finding new nodes, and you get a really long text or really long stack, all of items. So you'll need theta v memory to remember v recursive calls. And chances are in a spindly graph, you're going to have about theta v total nodes in your worst case path. Meanwhile, if you have a really bushy graph where most of the edges exist, then breadth first search is going to be really bad, because in a breadth first search, you need to store all of the nodes that are in your fringe, kind of the nodes that you've seen one end of, but you haven't looked at yet. So because of that, your queue gets really, really long. You can imagine that you have one node that's connected to like a million other nodes. All of those million nodes get connected and inserted into the queue, whereas with the depth first search, you're only looking at like a call stack of size 2 at that point, every single time. Now, we did need to spend theta v to track dist2 and edge2 arrays, but as it turns out, you can probably optimize this into a map instead of an array and save some memory that way. We won't cover this in detail in this class, just know that it is possible to save some memory if you do that. Now, breadth first search isn't necessarily good for finding shortest paths in the real world, though. Kind of the reason why is that it optimizes the wrong thing. It's a good heuristic to get the fewest edges to node, but it's not necessarily the shortest path. Let's take a look at a quick example. Here is a graph of an area on campus. Anyone recognize this area? First Memorial Mining? Yeah. This is kind of the Google Maps drawing. And here's an approximation of the graph that you might see if you convert this into an actual Google Map style graph. How do you want to go from point S to point T? What path do you want to take? And a second question, what path will breadth first search tell you to take? Let's try and discuss that. I'll come back in like 2 minutes. I just had a picture here. Yeah. I never had to do. Remember, either even back in the day. Yeah, even in my bread courses. Yeah, I just happened to get them right. They were all like nine essays. I remember seeing people with them, but somehow they were never a thing for me. All right. All right, let's have last thoughts. All right, let's bring everyone back. So, first off, how do people want to go from S to T? I'm going to start at S, and I want you to yell out directions. 10. So I'm going down this way. This is a bit too thin. Let me get a bigger width. This better? Yeah. 50. What 5? I do not see a 5. That's a 15. No, going down is a 15. All right, 30. 40. All right. That takes a total distance of how much? 90, 120, 130. Seems like a good path. Is this the best path to get from point A to point B, point S to point T? Yeah, I think so. I may have found a better one, but I feel like that's the right one. What path is breadth first search going to tell you to take? Breadth first search is going to tell you to take the path that takes the fewest total steps. There's 2 of them in this case, and we don't know which one's going to take, but I have a feeling that in the worst case, it'll tell you to go this way and then this way for a total length of 330. It's a length 2 path. Which one do you want to run, red or blue? The red run is healthier for you. Yes, but what if you're running late? Blue. Probably the blue one. All right. Yeah. Okay, these were the right paths. So breadth first search is going to yield this really, really long path that takes a really long time to get through. That's not a good path to take. Meanwhile, the one that we do want to take is this really shorter path that takes 130. So we're going to need a new algorithm, not just breadth first search, that takes into account the distances along each edge. The main reason why breadth first search didn't work was because it didn't care whether or not this length was 10 or this length was 260. It treated them all as the same for its weighing purposes. So how do we write an algorithm that actually takes that into account? Now, what we'll do for kind of the rest of this lecture is we'll be building up on this. So first off, let's try to get some intuition behind how you might build these shortest paths. Let's do this with some examples. Let's start with this. What is the shortest path from town A to town F on this graph? Each edge has a distance, kind of signaling how difficult it is to travel. For example, going from C to F, you have to cross these mountains, and I don't want to cross these mountains, so it's 15 weight. So our goal is to get the minimum weight to get from A to F. Let's take a few seconds to try and figure this out. Yeah, and keep in mind that these arrows are directional, so you can only go each arrow in one direction. All right, let's bring everyone back. What do people say is the best path? Best path. A to B to E to F. I say this is right. Yep, this is the right path. Now, the path from A to C to F, it was only 2 edges, but it's going to be a longer path. So sometimes we do want to go through more nodes to get to our target if it's a shorter path.
Also, you can go from C.
You can't go from C to E because C to E doesn't have an arrow. It has an arrow from E to C, but not from C to E. Yeah. You can kind of imagine that these are like one-way roads. Now, one thing you might notice is that this path, no matter which nodes you're going for and which graph you're working with, you'll never have a cycle. Assuming that all of the edge weights are positive, this is going to be true. Why is that the case? Can anyone give me an intuitive explanation as to why you'll never get a cycle in the shortest path? Yeah. Yeah. If you go back to where you came from, then you're taking extra time to just get back to where you started. That's not helpful in any respect. So you can just imagine you just take that cycle and remove it entirely, and you have a shorter path. Yep. Now, let me ask you a different question. What happens if we try to draw the shortest path from source A to every other vertex? And let's first assume that there's only one unique shortest path for each node. Let's try and draw that out. Let's start off with A to A. So what is the shortest path from A to A? 0, just go A. What's the shortest path from A to B? Length 2, and what does it do? You just go A to B. All right, let's pick another color. What about from A to C? Yeah, just this path from A to C. What about from A to D? 7. How do you get 7? That's not the right direction. 11? How do you get 11? A to B to E to G to D? That seems right. Is that right? Let me look ahead. Yeah, that is right. All right. What about to E? A to B to E? Yeah. F? ABF? We already showed that. And what about A to G? ABEG. Yep. Just for completeness, I'm just going to add the path from A to E or A to A. That just stays here. So this is kind of our total graph. What do you notice about this? Anything you notice about the sum total of all these paths? Maybe someone in the back? Yeah. Yeah. They all kind of follow the same path and then branch out. Does anyone have an intuitive explanation as to why that might be true? Someone new, ideally? Yeah.
One go from like node A to node B, and then from node B to node E. Or sorry, from A to E is the same thing as going from A to B and then B to E. Basically, the shortest path from A to B has to include the shortest path to the intermediate node.
Yeah. In effect, if we want to get to node E, we need to first get to one of the nodes starting from it, either node B or node D, I think. Those are the only two edges going into E. So in order to get from A to E as quickly as possible, we first need to get from A to B as quickly as possible, or we need to go from A to D as quickly as possible. In this case, the path from A to B is faster. So we go A to B as quickly as possible, and then we take a single jump to E. So that indicates that generally speaking, we're going to want all of our shortest paths to have other shortest paths as intermediate steps. You have a question or?
Uh, I was just gonna say, could you also just say that, like, the reason we get this path in general is because there are some nodes that happen to be very, very close to all of the other nodes. So if you're trying to go from like A to some other node, there's a decent chance you'll want to go to E first because E, or like B because E happens to be.
Well, yeah, in this particular graph, E did happen to be kind of in the middle of the shortest path on a lot of cases, but that's not necessarily going to be the true for like general graphs, right? Yeah, it is true in general graphs that in order to get to some node, you first need to get to the shortest path of a previous node, unless you're like at your current like state. If you're going from A to A, you don't have a previous node to go to. Otherwise, yeah, you want to try to take the shortest path first and then go one step further. So all these shortest paths tend to overlap. In fact, we can actually say that the solution is always going to be a tree, a subtree of the graph, because of this property that whenever we want to take a shortest path, we first take an intermediate shortest path. You can kind of think about this as the union of the shortest paths on all the vertices, right? If I take all of these colors out, then you can see this black bolded arrows. They form a tree that composes all of the shortest paths of this graph. Now, you could get non-trees if you have non-unique shortest paths, right? You can imagine that this graph had like all the edges of length 1. There might be a few like ambiguities there, but you can always pick an idealized or preferred path to give you a tree. So in general, if you're trying to find the shortest path from one node to every other node, then you'll end up forming a tree. And we'll call this the shortest paths tree. So here's a quick question. If you have a shortest paths tree, how many edges are going to be contained in this, assuming that all the vertices are reachable? V minus 1? Why do you say that?
You could want like one edge to that vertex. So if you go up toward the tree, it would just be minus one edge.
Yeah. One way you can say this is that if you have a tree that has V total vertices, then kind of each time you add an edge between two things, you're connecting two things together. So you have one fewer connected components. In order to get a tree, you need to get everything down to a single connected component, which needs a total of V minus 1 edges. Yeah. So overall, you will have V minus 1 total edges in our shortest paths tree. And that's going to be always true regardless of the graph you're working with. Yeah. Yeah, it's also true for any graph or any tree, right? Any subtree that is embedded within a graph is going to have exactly V minus 1 edges. Yeah. Just because a tree, by definition, has V minus 1 edges. All right. Now that we kind of have some intuition behind what we're trying to do, let's kind of come up with some algorithms to create these shortest path trees. What we're going to do is we are going to start off with some bad algorithms, and we're going to build from there. So now, first off, let's take this as a toy example, where we're trying to find the shortest path tree starting from A. Let's take a minute to figure out what the shortest path tree is going to be for this graph. Feel free to talk to your neighbors on this.
I've never seen it. I don't know where it is. There's a whole.
All right. What did people say on this? Uh, what edges do you want to add in your shortest paths tree? Yeah. Sorry, I can't hear you quite. The one from A to C, C to B, B to D. Yep, that forms a tree. Every single edge is, or every single node is accessible using these. And if you look, the shortest path from A to C is this, the shortest path from A to B is this, and the shortest path from A to D is this. Yep. This seems like a good approach. Here is kind of an annotation of this. I'm marking in magenta the shortest distance from each, the distance of the path that gets taken. So let's create some algorithms to find the shortest path. We'll start off with some bad algorithms and we'll improve it over time. And we'll start off with the algorithm in this state. In this state, we haven't found the shortest path to anything. So all the distances are infinite. And we don't have any edges in our shortest path tree yet. We'll kind of build the shortest path tree one edge at a time. So the first algorithm that we're going to come up with is just breadth first search. We've already said this is not going to work, but let's kind of see why it doesn't work to see if we can get any intuition behind it. So what do we start off with in a breadth first search? A, we start off by looking at A. So we look at A, and A, when we remove it, what is its distance? 0. Yeah. What do we do next? Yep. We're going to add B and C to our list. Did I forget to add the 0 line there? I might have forgotten to add the 0 line. But in any case, now the distance from A to C is 1. The distance from A to B is 5. What do we do next? Yeah, we look at B, because that's the next thing on our fringe. And we say that we're now looking at all of its paths from there. What is its best path, or to the remaining node? B to D. And we find the path there. And using that, we're going to end up getting a path of length 7 to D. We don't check a path from B to A because we've already found a path to A, so we're done with that path. We're done with that node, sorry. We then remove C, and then D. Nothing really happens at this point because we've already found paths to everything. We've already said these are our best paths. We're done. Are these our best paths? No. Why are these not our best paths? What went wrong? Yeah, in the back. Yeah.
You didn't consider that there would be a faster way to get a B instead of just going directly to it.
Yeah, we didn't consider the possibility that we may have found a faster way to B later down on this line of thinking. In effect, what ended up happening was that the algorithm that we started with, it took every node 1 edge away, then every node 2 edges away, then every node 3 edges away. And it would have worked if all the nodes were the same distance apart, like all the weights were one. But it doesn't quite work when the weights aren't all of the same value. Yeah.
You just do like a special BFS for each of those like just we count their distances like
Could you do a special BFS where each where you count like the distances?
if you rank it.
Maybe keep that in mind. Uh, let's take a look at another possible example. And the idea is, well, since breadth first search does work when all the edges are the same length, let's just do this. I'm replacing now an edge of length 5 with a bunch of mini nodes that have each length 1 away. All right. And the idea is if we can create this second graph efficiently, and we can run BFS on this second graph efficiently, then breadth first search should give us the right answer. So let's kind of run through our breadth first search, see if it works. We start at A. A is 0. What do you do next? Yeah, we add these two. I'm just going to show that they happen at the same time because it doesn't really matter the order in which they happen. And then we look at the nodes that are 2 edges away, which are these. And then 3 edges away, 4 edges away, 5 edges away, and then we're done. Did this yield the correct graph? Yes. Can anyone think of anything bad with this approach? Yeah. Memory? Tell me more. Yeah, we're creating a lot of these dummy nodes for no reason. That seems like it's going to be inefficient. Any other issues? Yeah.
If we have a really large number and already found the path to like B, we'd still go down the really large number of B.
Yeah, imagine this 5 was a 5 million. Now we've got to go through 5 million steps to get to B. That's going to take a while. Any other issues? There's one other issue that I came up with. Yeah.
There's also time you're gonna. I don't know if the other person was talking about that, but also the time to create that graph as well.
Yeah, time to create the graph as well is going to take a lot of time. Yeah. In effect, imagine that you had this graph where instead of miles, I just multiplied everything by the number of inches in a mile. This is not going to be a fun graph to build because now I have 316,800 nodes to put in between A and B. And that's going to be really annoying to deal with. The other minor thing that you might not have considered is what happens if we have fractional values, right? Like imagine that you had 1.5 as the distance between A and B. How do I create 1.5 nodes there? Doesn't feel possible. So we are going to end up being limited to integers if we try to do it that way. Yeah. But it did work. It was slow, but it did work. So let's take a look at some other approaches. The algorithm 2, we can kind of call this the best first order, right? We're looking at nodes 1 distance away, then nodes 2 distance away, then nodes 3 distance away. So let's try to visit the nodes in the same order as algorithm 2 did, but without creating those dummy nodes. Here's our new algorithm, similar to breadth first search, but what we'll do is we'll remove the closest edge from the fringe each time. So we'll use a priority queue to track the closest edges. That does mean it takes a bit more time. A priority queue takes log n time instead of constant time like a regular queue does. So we are losing a bit of time, but log n is a small enough factor. It probably shouldn't matter too much for us. So let's run this. I'm going to remove the closest vertex from the fridge. What is the closest one? Well, A, right? I'll remove the closest one first. But I add C and B first. And then I remove the closest. What's the closest? C, because C is the closest one to A. So what I'll do is I'll remove C. And then what I'll do? Well, I've already found a path to B, so I don't need to look at there. But I do need to find a new path to D. So I find a path to D this way. What do I do next? I move B. B, does it have any children that I haven't found a path to yet? Nope. So that's good. What next? D. And does D have anything I need to look for? No. Did this work? No. Why did this not work? Yeah. Ultimately, we're still running into that same problem from earlier. We didn't look for better paths once we found a path. We said we found a path and then we're done. That is not going to quite work for us because maybe we find a better path later. On the other hand, we did visit the nodes in best first order without creating the dummy nodes. We did end up getting the wrong result. The main issue here is that we took this 5 immediately. We were greedy and we said A to B is going to be the fastest. But in reality, if we'd waited just a bit longer, we would have found this path from A to C to B. And that would have made it better. So what we're going to actually do is we're going to change this slightly into what we actually are going to be using. It's called Dijkstra's algorithm. And the idea is instead of just looking at the best node and just immediately taking an edge, we're going to take it tentatively. We're going to say this path from A to B is our tentative best path, but we're still going to be looking for better paths later. If we later find a better path, then we are going to pick that instead and overwrite the old fastest path. This is kind of called relaxation. We're kind of relaxing to a better path. Don't ask me why it's actually called relaxation because I actually don't really like that name. From what I understand, it doesn't really have too good a reasoning in this particular context, but there are other contexts where it's useful to call it relaxation. But we'll be using a priority queue to track these best known distances, kind of improving as we go. Now, we will have to do some extra bookkeeping. Instead of adding to the fringe as we go, I'm going to try and add all the nodes to the fringe. You don't have to do that. You can imagine that just anything not in the fringe is considered infinite distance away. But for simplicity, I'm going to show that everything is in the fringe at the start. If you're worried about memory, you can fix this in later iterations of this. So let's start it up. We're going to start by A, right? And what do we do first? Yeah, we add B and C. And right now, these are our best paths. C takes 1 unit to travel. B takes 5 units to travel. What do we do next? What's the next node we look at? C. C because C is the closest node. And what do we see? We see a path to B that takes 2 distance. So I'm going to update B to instead be 2 distance away, not 5 distance away. And we find another path to D. What's that distance? Well, what's the total distance from A? 6. Yeah. So what we'll do is we'll update this. Now the path to B takes distance 2, and the path to D takes distance 6. What do you do next? Which one is better? B. I should have replaced this 5 with a 2. Something to fix for next time. Yeah. What do we see at B? We see a path to D. What's that distance? 4. Is that better than 6? Yes. So what do? We update the path to D to include this. And now we have a seemingly good path. Now we look at D because we have to finish everything. Does D have anything outgoing? No. So we're done. We have no more outgoing edges, so we don't do anything. And we have found our shortest paths tree. Is this correct shortest paths tree? Yeah, seems like it is. Do you think this works all the time? Is this going to work on this graph? What do you think? Yes? Why? Because it's weighted? Maybe because it's actually named, and if someone had a name for it, then it probably works. Yeah, let's take a look. Let's try it out on this bigger graph. What do we do first? Look at A. We add the edges to C and B. And I'm going to note it down on this like auxiliary array, kind of showing which the values for disk 2 and the edge 2. This thing on the left is kind of the array version of the thing on the right. It's just the same thing. It's just better bookkeeping. What do we look at next? C. What do we find if we do that? A path to an F of distance 15. So what's the total distance to F right now? 16. So now we add this. What do we do next? Go to B, because B is the closest one. What do we find? Path to D. How long is that? 13. Path to E. How long is that? 5. What else do we find? We do find a path to C, but what's its distance? 7. Do we do anything for that? No. It's a worse path than what we've already found. I don't want to use that. So I'm only going to look at the paths to D and to E, and then focus there. Yeah.
Reason why I went to C first.
Is there any reason why I went to C first? Yes, because C is the shortest path. C has distance 1, B has distance 2. Yeah. All right, what do we do next? What's the next thing we want to look at? E. All right, what do we look at from here? Or what do we find? F, what's its distance?
9.
5 plus 4, that's 9. G? 5 plus 5, that's 10. Yep. We also find a path back to C, but we don't care about that. We've already found a better path. All right, so what do you look at next? Yeah. Well, what do we look at next? Sorry. F, because F is the smallest value. Uh, do we have any outgoing paths from F? Nope. So that one's done. What next? G? Are there any outgoing paths from G? Yep. What's that path? Up to D? Is that a better path? Yes. So we update there. And then finally, we look at D. Is there any paths to improve from there? No. Now, one thing you might note is that every time we looked from a node to a new white node or to an older white node, we never improved upon the path. Is that going to be true in general? Regardless of what graph we're dealing with, is it always true that we'll never find a better path going to a white node? No? Why not?
Negative weights.
If you have negative weights, yes. But what if you have no negative weights? No still? Why not? How many people think it is true that it is going, okay, it is listed as impossible here, but but why is it true that you'll never have a better path, I should say? Yeah.
Because that node no longer exists in the frame, so we already found the shortest one. There's nothing to replace it with.
The node no longer exists in the fringe, so there's nothing to replace it with.
We found the shortest.
Well, that kind of does assume that like this works already. Yeah. Any?
So like if you already lose C, C is already the shortest thing when you consider it. And anything else, like if you want to go from E to C, you must add additional weights, which will only be bigger than C.
That's a good reasoning. Yeah. If we only have positive edge weights, then it's never beneficial to take a longer distance. C is already the first thing we removed, which means that by the time we're looking at any other nodes, we've already traveled a longer distance than we had to take to get to C using the path we found already. Yeah.
It's on a practical level. How are you updating like the distances?
How are we updating the distances?
Like, you know, I went from A to C and
yeah.
Like, how would you find?
How would we practically update these distances? We will get to that in a brief bit. I think the idea here is within this dist2 array, it's just changing a number. Within this fringe, you do have to add a new operation to your priority queue called update priority. As it turns out, that is possible to do in logarithmic time. It's a good exercise to try it out. See if you can figure out how to do that. Yeah, but it is possible. And for this class, or for this part of the lecture, that's all we need to worry about right now. Yeah. So continuing what you were saying, right? if we've removed C from the fringe, then that means that C is a shorter distance than anything left on the fringe. And that means that if we go to any of those other nodes and then take more distance to get to C, then that means we've already traveled longer than our original path to C in the first place. So that means that every time we remove something from the fringe, we are already finding the smallest thing. So here's kind of like the formal definition of this. If you look at the relaxation process, the edge 2 is always the best known path. The dis 2 is the best known distance. And the priority queue contains all the unvisited nodes. And we're always visiting vertices in order from the total distance from the source. So whenever we travel further from that, we're always have already found better paths. We look at better paths before we look at worse paths. So we never have to relax on a white node. Now, this is true only for non-negative edge weights. We will look at this. Yeah.
I'm just going to ask, in general, if there's two shortest paths, is there a way to like...
If there's two shortest paths, if there are two shortest paths, you can generally pick arbitrarily. Either way, you'll end up being able to get a tree. It kind of doesn't matter which one you pick. You can imagine, for example, that you kind of perturb the graph slightly to make one slightly heavier, slightly lighter, and you'll get the same result, right? But with unique weights. Yeah. You can kind of do this proof using induction, which is kind of what we were talking about earlier, right? If we look at C, then everything else is already greater than C, so we'll never have to find a path that does better. So you can kind of steadily grow the set of nodes that you found that have the shortest path until you find it better. Kind of the same reasoning. It's doing the same thing as when we had a bunch of these dummy nodes, but instead of creating the dummy nodes, we're just counting how many, at what point we are going to remove these nodes. Yeah.
I guess I was trying to ask, like, let's say you have a graph and you know that there are multiple shortest paths. You want, I don't know, just compare several graphs, figure out which one has the most number of shortest paths. Could this still be used for that? Is that...
Can you determine from a graph the number of shortest paths? It is not currently known whether that's possible. This is actually one of the problems that is considered really hard, and if you solve, you will earn $1 million. So come back in lecture 39, we'll talk about that. Now, if you have negative edge weights, as you mentioned, it is possible to do better by taking a longer distance, right? You can imagine that you have to go a longer distance and then take a negative edge to get a shorter distance total. So this isn't actually going to work with negative edge weights. So here is an example where relaxation might succeed, even though we're going to a white node. This doesn't happen in the cases of non-negative edge weights. And because of that, Dijkstra's does work for non-negative edge weights. Yeah.
Why would you ever have a negative?
Why would you have a negative edge weight? That's a good question. Who knows? One option is maybe if you're like taking airline flights and your airline is doing a promo where if you take this particular flight, you get it for cheaper. Or maybe you like save money. I don't know. You might find reasonings in other contexts. Normally speaking, negative edge weights tend not to happen in reality. But there are good reasons why you might want to use them in a graph. Yeah. So Dijkstra's doesn't work for negative edge weights. In fact, if you manage to find an algorithm that works efficiently for negative edge weights in general, then that is also one of the $1 million problems. Yeah.
Same weight to everything, so everything's non-negative.
Can't you add the same weight to everything so the answers are non-negative? No, you can't. And the reason why is if you go back to hang on. If you go back to this graph here, right? Imagine if you add, let's say, 100,000 to every single edge here. Then the path from A to B to E to G to D is going to take 400,000 extra time. But the path from A to B to D is going to take 200,000 extra time. And that means the path from A to B to D is going to be preferred in that case. So you're not necessarily going to get the same result by adding a same constant to everything. So you may end up getting different results. Yeah.
Building on that, if you were to multiply every path by some constant, that would not change the shortest path, correct?
If you were to multiply it by constant on every path, I believe it shouldn't affect things. I'd be happy to hear your proof as to why that's the case after lecture. All right, let's go back here. Let's try and figure out the runtime of this. Since we don't have too much time, I'm just going to explain what the runtime is total. Yeah.
By -1.
Can you multiply everything by -1?
No negative.
You can't multiply by negative numbers.
If it was negative, multiply by.
If you multiply everything by -1, then you turn all the shortest paths to longest paths. And longest paths to shortest paths. So you can use this to get the longest paths on a graph where everything is negative and you have no positive edge weights. But that's kind of getting into territory of I'm not sure when that might be useful. Yeah. Anyway, let's take a look at all the runtimes of this. For adding things into our priority queue, it's going to take log v time to add everything. So that's a total of O of log v time. Well, v times you add, each one takes log v. Now, to remove the smallest, how much time does it take to use remove smallest in a priority queue? Log the number of items. So you'll have log v time. There's only up to v vertices in that. And removing the smallest, you have to do it a total of v times. So you have v log v from there. How about change priority? How often do you have to change the priority on a node within your priority queue? Well, in the worst case, each edge causes one more relaxation. So it's upper bounded by E times that many operations. We don't know the exact value there, but we know it's upper bounded by E. Yeah.
How do you actually change priority like
How will we actually change priority in min heap? Good question. Come to me after class, we can discuss this. There is a way to do this in log v time using the tools that we have already discussed in class. Yeah. And overall, if you look at this, you end up having v log v plus e log v. You have technically two of these, but it doesn't matter because we remove constant factors. Now, if we assume that e is greater than v, which is going to be true for connected graphs with at least one more edge, we can say that it's just O of e log v. So our total runtime for Dijkstra's is going to be e log v, which is effectively as efficient as we can get. It's fairly good. Now, is this good for navigation in general? Is it going to find the shortest path? Yes. Is it going to be efficient at finding the shortest path? If I want to say go from Denver to New York. Hopefully. Well, here's an issue. If I'm in Denver, we're looking at paths that go from shortest to greatest, right? And it's going to work well to find the shortest path from Denver to everywhere else. But that means that if I want to find a way from Denver to New York, first I'm going to look at every other path that takes me to a place closer than New York. Do I want to use the fact that going from Denver to Los Angeles is really good before I find a path from Denver to New York? Not really. Dijkstra's is going to explore every place within 2,000 miles of Denver before it even tries to get to New York City. And that's really, really slow. I don't want to look at every single path before. I want to kind of focus on New York if I'm just looking for that path to New York. So how do we do better? Well, we might say, let's explore in that direction, maybe. I don't want to go west to go to New York because I don't think that's going to be better. If we want to formalize this, what we're going to say is that we're going to add a heuristic. A heuristic is kind of a model of how long we expect it to take to get that far. And the idea is if we add this heuristic to Dijkstra's, then we can actually do better. We can kind of ignore paths that are going to take us farther away and find the path to G that takes us closer. Here's kind of a full demo. I don't have the time to go through it, but the idea is if you add this heuristic value, then we can get better values as to how close things are. in effect, instead of just looking at the numeric value of how far we traveled so far, we're also adding an expectation of how much time it takes. So we're looking at the best first, where best not just includes the distance so far, but also the distance to the target. Yeah.
How do you get these numbers?
How do we get these heuristics in the first place? Good question. Well, as it turns out, the runtime of A star is going to depend on how you get that. Dijkstra's is kind of like a heuristic where you just give zeros to everything. And that could be an optional heuristic you can use. It works for every graph. As it turns out, you don't need any specific heuristic. Any heuristic works as long as we have certain properties. Kind of as a quick overview of A star in the future, these are kind of the properties that you need to get a good heuristic. The most important one is you just need to be able to underestimate the distance. So as long as your distances are always less than or equal to the true distances, your heuristic is going to let you to work. In a graphs or a map algorithm, kind of the best way to do that is to just take the crow's fly distance, the distance as the straight line distance on a map. Because that's always going to be better, or it's going to be better than the actual distance to the real path. If you do this wrong, then you do end up saying that Illinois is the bad place to go to. So you end up just traveling around Illinois instead of through Illinois, for example. So you don't want to do that. It is going to end up causing incorrect results if you try to do that. But overall, as long as you get these results, you are going to end up getting an algorithm that works the same way as Dijkstra's, but is faster. Not asymptotically faster, but truly faster. It does kind of depend on the heuristic, though. All right. If there are no other questions, I think I'm out of time, so let's finish up. Yeah.
One question.